All right, so moving forward with solutions, we're going to start talking about the idea of molarity. So one of the most important properties of working with solutions is this fact that we can make solutions with different concentrations. You can make a lot of dissolved solute in your solution or not that much dissolved solute. What that allows us to do is easily control the properties of a solution. Just say something like food coloring. We can put a little bit of food coloring, or we can put a ton of food coloring. And importantly, this is a property that we can control. You can affect the properties of solutions. You can't change the color of pure food coloring. It's just red. It's very dark red. But if you dissolve it in water, you can make aqueous solutions, all sorts of shades of red. Is there barely any solute particles moving around, or are there a lot? And we use this concentration, and we always get a ratio. It's amount of solute per amount of solution. So this is going to be a ratio that is always going to let us talk about how much stuff is dissolved in a given volume of solution. The concentration unit of choice in chemistry is molarity. The symbol for molarity is going to be a capital M. Oftentimes you'll see it written as bolded M. I can't do that in my handwriting, so I just use capital M. The book does use a bolded M a lot. You see a lot of other resources doing that. But capital M, I'm going to use capital M here and in my when I handwrite any sort of thing. But that is what that means. And the definition of molarity is the number of moles of solute dissolved in 1 liter of solution. So we said that concentrations are always amount of dissolved per amount of solution. Here, the amount that we choose to use is moles, and the amount of solution we choose to use is volume, specifically liters. So it is always going to be liters of volume of our solution. That may not be what we normally measure volume in. Milliliters is a lot more common in the lab, just in terms of what's reasonable. But volume is what we want to use in molarity. Conversationally, when we're talking about molarity, so say I had a concentration that was 2.0 and then capital M, so 2.0 molarity, we would kind of conversationally say or just talk about that as 2 molar. So just like the tooth, 2 molar means the molarity equals 2. If you say 2 molarity, that's fine, but I will say 2 molar. And what I mean by molar is that is the concentration in molarity. So the reason why we use molarity is the motivation for solutions, we said, was to do reactions, right? To facilitate chemistry. And what we really care about then is the number of dissolved molecules. So that's why we don't want to use a mass of solute. We want a counting unit of solute. We don't want to talk about individual molecules. We want to be reasonable. And that's why we're going to use number or moles, which gives us a counting unit amount of molecules. So if, say, I have different solutes in these top row, I have, say, this orange solute, this blue solute, and then kind of pinkish solute. And we can see that in these cases, they have the same molarity. So it doesn't matter what the molecules of solute look like. For a given solution, there is the same number of molecules in that volume of solution because the molarities are all the same. Okay? If I have higher molarities, I would expect more dissolved molecules. This number of solute molecules increase. So for a given solute, higher concentrations in molarity mean more dissolved molecules. But importantly, for different solutes, I know that the number of molecules dissolved in a given volume will be the same if the molarity is the same. So that's really what we care about. Number of things present for doing reaction, number of molecules, number of atoms, and molarity lets us measure that. If we used a mass amount, they would be dependent on what we're looking at. Let's look at an example of computing the molarity of a solution. A 400 milliliter solution contains 56.3 grams sulfuric acid, H2SO4. What is the molarity of the solution? So if we start by asking, what do we want? You can see that it's molarity. And importantly, molarity has an equation associated with it. So don't worry, there will be plenty of unit conversions still. But when we're dealing with molarity, if we want the molarity or we're given a molarity, there's always an equation associated with that. So really, if we want molarity, the question is, what are the moles and what is the volume of solution? So with that equation, we can get those necessary variables, moles of solute, volume of solution. Maybe worthwhile to ask, what is the solute? And in this case, it would be sulfuric acid. You'll note in this case, it says the solution contains sulfuric acid. That means that sulfuric acid is dissolved in the solution. So we want moles of sulfuric acid and we want volume of solution. We can say that we're not given moles of that sulfuric acid, but importantly, we are given mass. This would be the most common way to do it. You made this solution, you measured out some mass of solute, sulfuric acid in this case, the H2SO4, and you need to turn that into moles using the molar mass. Your volume of solution is given, but it's in milliliters. Whenever we are working in molarity, that volume needs to be turned into liters. So molarity problems combine the molar mass conversions we just learned with a nice refresher on metric conversions that we learned previously. So doing this process is going to be kind of our standard approach to computing molarity. This is a very common issue. You generally measure volumes in milliliters and you generally measure amount in mass. So you need to do 2 conversions and then you can plug into your molarity equation. Let's go ahead and do it. 400 milliliter solution contains 3 grams of sulfuric acid. What is the molarity of the solution? So when we want that molarity, whenever we're given molarity, that's great because molarity has an equation associated with it. We know that molarity, in this case, is equal to, it's going to be moles of H2SO4 divided by liters of solution. So this is what we want. So the question is, do I just have the moles of H2SO4 and the liters of solution? The short answer is no, but I'm close. Okay, because in order to get this moles of H2SO4, that's an amount of H2SO4 it's counting, I have a mass description. So I have 56.3 grams of H2SO4, which I can convert. It's not already in moles, but I can get it there. Then I have liters of solution. Okay, so if I have liters of solution, I want to I don't quite have that, right? I'm given 400 milliliters, which is close, right? It says volume of solution, just not the right units. So all I need to do is do some conversions here, and then I can plug them back in. So we'll start with, we'll go back, revisit some metric conversions. So I have 400 milliliters. I'm going to do a conversion. 1,000 milliliters for every liter. 0.4 liters. Okay, so that's based on our metric prefixes. Milli, it's a 1/1000th. So in 1 liter, I have 1,000 milliliters. More on topic, I have the grams to moles. Now I want to use the molar mass for H2SO4. For H2SO4, that is 98.08 grams H2SO4 per 1 mole H2SO4, giving me 0.574 moles of H2SO4. This molar mass, I just went ahead and calculated that myself. .08 grams per mole, right? So it's always a 1 next to the mole. The number is next to grams. We are seeing these molar mass conversions are not going anywhere. So now that we needed moles of H2SO4, check. We had liters of solution, check. I can plug them back in. and we can get that molarity is 1.44. And if we look, the units we'd end up with are moles per liter. Those aren't going to cancel out, but we just write that as 1.44 capital M. So the whole, this entire thing, moles per liter, just becomes capital M. So whenever we're asked for molarity, we have an equation associated with that we can use. This equation we can use, whenever asked for molarity, we can use this equation. And then oftentimes, this is a realistic depiction. You'd measure a mass of solute in grams. A liter of solution in a chemistry lab is a lot. So normally we measure in milliliters. 400 is still a lot of solution. So normally we need to do this conversion of milliliters to liters, grams to moles using the molar mass. And then we can take those, combine them back together into the molarity equation, and get our answer. So this is, it may seem piece, but this is really kind of the practical, this is what you'd end up with. There are times where you have, moles and liters of solution, and you just combine them in the equation. But it's very common to have grams and milliliters and need to do these conversions to get the answer you're looking for. Participation 6-9, question 1. You dissolve 0.45 moles NaCl in enough water to make 230 milliliters solution. What is the molarity of this solution? Is the first question on participation 6-9 due Tuesday, June 9th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, you dissolve 0.45 moles NaCl in enough water to make 230 milliliters of solution. What is the molarity of the solution? Okay, our first participation question for 6-9 was in this video. Got a couple more videos left. I bet you we'll find some more questions on that participation assignment. See you in the next video.